Hi there. Well, this is my first attempt at trying to make some videos for AP Physics, and I'm using a new software, so try and be patient with me, but at the same time, I appreciate your feedback. So let me know what's working and what isn't. In this unit, we're covering simple harmonic motion, and this can be anywhere from ideal pendulums to springs going back and forth. And I think you're going to see a lot of similarities between simple harmonic motion and uniform circular motion. So this lists out all of our objectives, but this video is really going to just talk about the conditions that are necessary for simple harmonic motion and talk about frequency and period, and maybe just go into a little bit in terms of energy that is involved in harmonic motion. So I'm going to work 3 example problems in this video, and we'll see how it goes. All right, so simple harmonic motion is oftentimes abbreviated as SHM, and it's any time an object is displaced in a way that the force that takes it out, whether it be on a spring or a pendulum, eventually brings it back into what's called a restoring force. So it's an oscillating motion, and it's periodic, so that means we can determine frequency and period and so on for this. So examples of linear restoring forces could be a mass on a spring, like I talked about, a pendulum on a clock, a tree limb maybe coming back and forth after you rush by it or after the wind blows it or something like that. A child on the spring, I think you get the idea. But anything that is moving back and forth in a repeated motion that has a restoring force to bring it back to an equilibrium position. So the first thing that we're going to look at is a block on a frictionless surface. So we have a spring that is attached to, sorry about that. So we have this right here, we have a block that's attached to a spring that's going to be oscillating back and forth between this A and this A, back and forth. Now, not that you need to worry about it too much up here, but there is something up here that is talking about angular momentum that's happening up here. That said, we haven't covered that just yet, so you don't have to worry about that so much. So when this block is being displaced back and forth, it is the X motion of this is actually going to mirror what we would see in uniform circular motion. So simple harmonic motion, as I said earlier, closely resembles uniform circular motion in a lot of different ways. It's just that simple harmonic motion describes one dimension of an object that would be moving in uniform circular motion. So any kind of horizontal spring block oscillator, something like this, that has a block with a mass that is sitting on a surface and attached to any kind of vertical wall or spring, something like that, with some spring constant K. The period of this oscillation depends only on the mass of the block and the spring constant. So a lot of times there's a misconception that maybe the more I pull on this, the more force, but actually the period that this goes back and forth is only dependent on this K and the mass. So just because I pull it out farther just means that it's going to have to move faster to keep up with this period. Now notice this equation over here off to the left, and it's in red, which means it is also on your laminated sheet. And if you look, we've got 2 pi square root of the mass of the object over the spring constant. So just looking at example problem number 1, it says a 5 kilogram block is attached to a 2,000 Newton per meter spring as shown in the displaced and displaced a distance of 8 centimeters from its equilibrium position. Determine the period of the oscillation and frequency and the frequency of the block. So we're going to use the same equation that we just saw. Ts equals 2 pi square root of the mass over K. So we're going to substitute in here. We've got the 5 kilograms over the 2,000 Newton per meter. And you should get a period of 0.314 seconds. Now, that said, it also says, and the frequency of the block. But if you remember, period is equal to the reciprocal of the frequency. So if we take our period of 0.314 and divide that into 1, we should get a frequency of 3.18 hertz. Okay, hopefully that makes sense. My writing is not what I had hoped it would be on, on the iPad, but again, I appreciate you bearing with me. Example problem number 2, it says rank the following horizontal spring block oscillators resting on frictionless surfaces in terms of their period from longest to shortest. So how we would approach this is we would use this same equation. We have the 2 pi square root of the mass over the spring constant. And you would solve that for each one of these. Now, I would suggest that you pause and at least try a couple of them. Make sure that you're getting the same numbers that I am. But over here at A, I got 0.888 seconds. Now keep in mind this period, just as a reminder, this is how long it takes it to complete one full cycle. And B, I have 2.35 seconds. C, I'm getting 0.199 seconds, and D, finally 0.444 seconds. So if I'm going from the longest to the shortest period, then I would have to rank this as B, A, D, and C. All right, so I want to cover one more thing before I look at a pretty massive example problem to wrap this up. And that's really talking about the energy that is going on during this oscillation. So energy of the spring block oscillator is going to be conserved as long as we assume that it's a frictionless surface. So the total energy is always going to be constant. Now that said, the kinetic energy and the potential energy is going to go back and forth in terms of what's being maximized. And you can think of this in terms of a pendulum as well. When a pendulum swings all the way to the left or right, it's maximizing its potential energy and minimizing its kinetic energy. And then as it swings through the center, its kinetic energy is maximized and the potential energy is minimized. And the exact same thing is happening with our block on the spring. So when the block is at its equilibrium position, so I'm talking right here, there is no elastic potential energy stored in the spring. So when it's at its equilibrium in the center, I do not have any potential energy in the spring. So all of the energy that's in the system is just kinetic. When the block is at its maximum speed, this is at the center, okay? When the block goes all the way and extends out at either end is when the potential energy is maximized, and therefore I will not have any kind of kinetic energy at that point. So again, maximum amplitude is what they're calling it here at C and B. That's all elastic potential and the kinetic energy is 0. And right here is where my kinetic energy is maximized. So there's a lot of different ways that you're going to see it. I did include a table that I felt would be helpful in terms of looking at this oscillating block system. We've got our maximum potential energy on either side, so right here and right here. And so at displacement, they're going to be maximized at B and C. Notice that one of them has a negative sign, and the displacement is 0. The velocity is at its maximum right in the center, and then I have 0 velocity at that instantaneous moment that they maximize on either end there. Kinetic energy is maximized in the center. We already talked about that. 0 kinetic energy on either end. The force is 0 in the center. So if we think about the force being maximized by the spring potential, it'll be maximized on the ends. And then acceleration is 0 in the center. It's when my velocity is maximized. Acceleration is 0 because it's not speeding up or slowing down. And then acceleration is actually maximized on the ends where the position changes, where I get a change in direction. We could also look at this in terms of graphs, and I've seen this several times now on our practice tests. If we're looking at the same kind of oscillating system where my potential energy is maximized at B and C, if you look, this is displacement. So if I'm graphing displacement, I see it's maximized at the B and C locations where the potential energy is maximized. The velocity is maximized in the center. My potential energy for the spring, there's only a positive potential energy and it's maximized again at either end, B and C. My kinetic energy is maximized at the A section. One thing just to note on a little side note here, my potential energies and my kinetic energy, notice there are no negative energies there, right? We can go down to 0 kinetic energy and maximize kinetic energy, but we're not going to have a negative. And I know we've talked about negative energy and how that doesn't exist. Our force is maximized where the spring potential is maximized at B and C. And finally, the acceleration, notice the acceleration is 0 right in the center, just as it is with the block. And the acceleration is maximized at B and C where it's changing directions. So again, I can see this presented in several different ways, but hopefully looking at this graph will help. All right, so energy and oscillation through this entire time interval. I just want to note here that the total mechanical energy of the spring block oscillator remains constant unless there's friction. Now, in reality, typically we're going to have some friction going on here, but things to kind of keep in mind. If friction is involved, then over time these oscillations will get shorter and shorter and shorter until it's not moving very much at all. That process is called damping or damped harmonic motion. And that has to be losing energy to friction. It could be sound, maybe some heat due to the friction as well. But other than that, assuming a frictionless surface, we assume that it continues on. All right, so here's this example problem 3 that I was warning you about. We have quite a few problems to try here. I have a 2 kilogram block attached to a spring, and a force of 20 newtons stretches it all the way to a displacement of 50 centimeters. So I've got my block here, and it's attached to a spring, and a force is being applied to pull it out in this direction, 50 centimeters. All right, so, and this guy is 2 kilograms. All right, so A says, what is the spring constant? So we're going to look at our laminated sheet here, and the laminated sheet tells us that force, this is A here, that the force is equal to K times X, where K is the spring constant and X is the displacement. So if I want to know the spring constant, well, I know the force that's being applied, so that was 20 newtons. And that is equal to the spring constant times the displacement, which we have 50 centimeters. Keep in mind we need to move that into meters. So I'm going to move this over 2 places to 0.5 meters. And I'm going to get a spring constant right here of 40 newtons per meter. The total energy. Well, I know that the energy is maximized at either end as spring potential or in the center as kinetic energy. Now, I don't have a whole lot of information here to do kinetic energy, but I can figure out what the spring potential is at either of those ends. So my spring potential is equal to 1/2 kx squared, which is equal to my spring constant that I just found, Newton per meter. And the distance that is being displaced is 0.5 meters, and I'm going to square that. And so I have 5 joules for a total energy here. Don't forget that 1/2 there. So 5 joules is being used, and this is going to help us later on in this problem as well, because 5 joules is when the maximum amount of energy, and that's going to be constant. So part of it may be in potential, part of it might be in kinetic. But again, the idea is that 5 joules is going to be our total. So the speed of the block at equilibrium. So at this point, you should kind of think to yourself, so at the equilibrium position, my speed is maximized, which means at the equilibrium position, 5 joules is all kinetic. So I'm going to put 1/2 mv squared there. And I'm going to set it equal to my 5 joules. So that right there, if it's all kinetic, and I'm going to just save space here. If I'm solving for V, my V should be 2.2 meters per second. I'm running off the side of the slide there. All right. These next two, though, are going to be a little more complicated. So the speed of the block at 30 centimeters and the speed of the block at negative 40. Notice that neither one of these are all the way out at our 50, and they're not at 0, which means both of these are going to be solved the same way, because my speed is going to be equal, or I should say my total energy is going to be separated between kinetic and potential. So basically my total energy, I'll just put ET equals my springing potential, so I've got some of that, and my kinetic. So my spring potential, we already know, is 1/2 kx squared, plus my kinetic is 1/2 mv squared. So I'm going to have to, and I'll kind of make some room here in a little bit, I'm going to have to put the potential right here, right, my displacement for my potential right there, and basically rearrange this equation to solve for my v. So I'm gonna suggest that you pause for a second and plug those in and make sure that you're getting the answer that I'm getting. At 30 centimeters, I'll put down here for D. At 30 centimeters, I got 1.8 meters per second. E, and make sure that you're using your 40 centimeters there. At E, I got 1.3 meters per second. All right, so that's going to take care of D and E. I hope that makes sense, because we did quite a few problems with energy and setting potential and kinetic equal to each other. So I'm hoping and making assumption that you're going to be okay with that. All right, so let's take a look at F. It says acceleration at the equilibrium position. Well, this might sound more complicated than it is, but if you remember, in the center at equilibrium, I don't have an acceleration. So my acceleration at that point is actually 0. The magnitude of the acceleration at 50 centimeters. Well, this, if you remember, 50 centimeters, this is where my acceleration is maximized because I'm changing positions. So at this point, F equals ma, and my ma, or my force, is all coming from my spring constant, which is kx. So acceleration, I'm going to kind of rearrange this a little bit. My acceleration, and actually that's going to be a negative kx over m. And so I'm going to put my spring constant at negative 40 newtons per meter times the 0.5 meters. That's my displacement at, and all over 2 kilograms, which is going to give me a negative, let's see here, G is going to be a negative 10 meters per second squared. All right, we've got just a few left, and of course, like before, I'm running out of some space, so I'm going to erase some of these and try this again. All right, so H, the net force on the block at the equilibrium position. At equilibrium, there isn't a net force. I've got maximum velocity, but no net force. The force is all at either end. Either end is where I've got maximum spring potential, and that's where the force. So this one, again, seems more difficult than it is, but that is just 0. Now my net force at 25 centimeters is solved the same way we've solved the other two. We're looking at force equals negative kx. We put in our spring constant, and the displacement at that point, remember we have to put this into meters, so I'm going to move this over 2 places, 0.25 meters, and I'm going to get negative 10 newtons for the force. Last but not least, it says, J says, the position where the kinetic energy is equal to the potential energy. So if I'm maximized on either end at potential energy and my kinetic energy is maximized in the middle, that means basically in the middle, in between equilibrium and the extended position there, is where I'm going to find where these two are equal to each other. So what I'm going to do is I'm going to put my kinetic energy here is equal to my spring potential. Hopefully that makes sense because my kinetic energy is equal to my potential energy there. And this is also equal to my total energy of 5 joules divided by 2. Again, I hope that makes some sense. And I'm going to set this equal to my potential, my spring potential. And the reason why is because the spring potential is giving me a displacement. So I'm solving for my x right here because I know I want 2.5 joules. Whenever 2.5 joules is equal to my potential, that's the displacement I'm looking for. So when you solve for x right here, you should get 0.35 meters. Now, this problem resembles very much a free response question that you might see where it goes through a series of steps on the same problem. Again, I would suggest that you pause, take a look at those, and maybe even try and work them again on your own. I hope this has been helpful, and I will try another video. Thanks.